Hey guys, in this video I'm going to run you through all the solutions for the 2023 Edexcel AS Level Maths Paper 2. Every question is going to be timestamped so you can easily jump to a question or rewatch it if you need to. Hope this helps. Okay, so here we are at the front of the paper. Question 1 is about the weights of plums and it's a histogram. It says, part A, can we estimate the mean weight of the 50 plums? So to get an estimate from a histogram for the mean, we need to use linear interpolation. So basically we're going to assume that every data point is evenly spread in each set. So the average is just the midpoint of each set. So we can take every data point basically as the midpoint of each set. So for this first set from 60 to 62, we can get the frequency by doing the area because it's a histogram. So that'd be 2 times 3. And then we're going to take every data point, so they're all 6, to be basically 61 effectively, as that's the midpoint of the set. Then repeating that for the next groups, we'd have 2 times 12 times 63. Then we'd have 2 times 8 times 65. Then we'd have 2, oops, that's a plus, 2 times 3, no, times 2 times 67. So that's the sum of all our data, effectively, and then divide that by the number of pieces of data gives us the mean, so over 50. That gives us a mean if we type it in the calculator, so let's use fraction, 2 times 3 times 61, plus 2 times 12 times 63, plus 2 times 8 times 65, plus 2 times 2 times 67, all over 50. Gives us 63.72. Part B says, can we estimate the standard deviation of the 50 plums? So first off, the formula for the standard deviation is the square root of the sum of x squared over n minus the sum of x over n all squared. So this is just the mean. We've already calculated that. And this is the average of all the squared values. So this was the average of all the regular values. If we want to get the average of the squares, we just actually square all these values. If I go back into my calculation for the mean and simply square the averages in each part of the calculation, we'll get the average of the squares. Check I've got all of them, which I did. So as a decimal, that is 4062.76. So this is going to be the square root of 4062.76 minus our mean from before squared, so 63.72, all squared in the square root. So if we do the square root of my answer from just now, minus 63.72 squared, then write that as a decimal, we get 1.59. The three significant figures. Then the last part, it says, later it was discovered that the scales used to weigh the plums were broken. Each plum actually weighs 5 grams less than originally thought. So basically all the true values of the plums should just be all shifted. All the data we've collected to get the true values, just shift them all by 5. State the effect this will have on the estimate of the standard deviation. Okay, so the standard deviation is a measure of your spread from the mean. So if you shift all the values by the same amount, then the mean is shifted as well as all the data, meaning the average distance of the data points from the mean doesn't change at all. So there'd be no effect, basically. So we'll say no effect on standard deviation. as the spread from the mean is unchanged, or the spread of the data. From mean, is unchanged. Moving on now to question 2. It says, Fred and Nadine are investigating whether there is a linear relationship between daily mean pressure and daily mean air temperature in Beijing using the 2015 data from the large data set. Fred randomly selects 1 month from the data set and draws the scatter diagram in figure 1 using the data from that month. The scale has been left off the horizontal axis. So it just says describe the correlation in figure 1. So for me, there's no real relationship. There's just one whole big cluster of data there, right? So that would be no correlation for part A. So part A will say no correlation. And let's keep reading. Now it says Nadine chooses to use all the data for Beijing from 2015 and draws the scatter diagram in figure 2. So that looks like it has some actual correlation. We've got like a downward trending relationship, so a negative correlation. Explain in context what Nadine can infer about the relationship between P and T. So I just mentioned it's negative correlation, but they say in context. So a negative correlation then for us means we can expect a decrease in daily mean air temperature with an if there is an increase in daily mean pressure. So can expect a decrease in daily mean temperature, it was, I think. Yep, mean air temperature. Mean air temperature if there is an increase increase in daily mean pressure. Okay, then it says, using your knowledge of the large data set, state a value of P for which interpolation can be used with figure 2 to predict a value of T. I think they would mean state a set of values for pressure where we can linear interpolate. So when you're going to linear interpolate, you have to be in the data range of your data set. Otherwise, you're extrapolating from the data set, which is generally something you don't want to do. And then they're testing your knowledge of the large data set. You're meant to know that the large data set for temperature runs from 990 to 1040 hectopascals. Okay, and then it says, using your knowledge of the large data set, explain why it is not meaningful to look for a linear relationship between daily mean wind speed and daily mean air temperature in Beijing. So that's, again, knowledge of the large data set and essentially to know what the data, how it's measured. So the daily mean wind speed is a qualitative variable rather than a quantitative variable. So you can't really have a correlation between something that isn't a number, strictly a number. So yeah, the daily mean wind speed isn't actually measured as a number. It's measured as like high, low, average. So a qualitative measurement or variable. So hence can't produce a linear relationship. Okay, moving on now to question 3. It says, in an after-school club, students can choose to take part in art, music, both, or neither. There are 45 students that attend the art after-school club. Of these, 25 students do art, 12 students take part in both art and music, and X number do music. Find the range of possible values of X. Okay, so I think this would be best visualized with a Venn diagram, right? We can see what we actually know. So let's say this is art. Make that a bit bigger on the intersection so I can write on it. So there's music. And we know 12 students take part in both. So 12 go in here. 25 do just art. 25 do art as a total, or 12 do both. That means 13 must just do art. And then we don't know the number that do music. So let's be careful here in that X is the total number. So let's call this number Y. And then we also know some of them can do nothing, it says up here. But we know there's 45 total. So if we create some relationships, well, we know that 45 is the total. So we know the 13 plus the 12 do art. So 25 plus the Y plus the Z must equal 45. And we know there's a minimum number of people that do music. So X must be greater than 12 because we know a certain number of people do both, right? So it must be greater than 12. And then if you think there's a cap, well, let's assume like the worst case scenario would be that there's 0 do neither, right? That would give us the extreme value for them to get as many people as possible doing music. So if none of them did nothing, then we would have Y. The biggest value Y could be would be 25. 45 minus 25, which would be 20. So then the biggest possible value we could have for people doing X would be 12 plus the 20. So that would be 32. And it could equal that. So X is greater than or equal to 12 or less than or equal to 32. Okay, then one of the 45 students is selected at random. Event A is the event that the student selected takes place in art. Event M is the event that the student selected takes part in music. Determine whether or not it's possible for the events of A and M to be independent. Okay, so for the events A and M to be independent, that would mean the probability of the intersection is equal to the probability of the product. So let's see of the events multiplied together. Let's see what that tells us about the possible values for X. So let's just write it down first. So probability of A intersection M needs to equal the probability of A times the probability of M if independent. So the probability of the intersection is 12 over 45. And then that would need to equal the probability of A, which is 25 over 45, times the probability of music, which would be, well, if we just use our value, let's just take X like we had in the question before as the total that do music, so X over 45. So if we solve this for X, we're going to be able to see if it lies in the possible range. So first off, if we multiply both sides by 45, we can get rid of one of the 45s. And then if we just rearrange, we could multiply by another 45 and divide by 25. So X would be 12 times 45 over 25. So plugging that through the calculator, we get see. Oops, 45 over 25. So we get 21.6, which is in the range, but it's a decimal. So that doesn't make any sense, right? We can't have 21.6 students be taking music. So not possible to have 0.6 of a student. Right, of a student. Therefore, they're not independent because we can't satisfy the relationship for independence. Okay, moving on to the next question, question 4. It says, past information shows that 25% of adults in a large population have a particular allergy. Ryland believes that the proportion that has the allergy differs from 25%. He takes a random sample of 50 adults from the population. Ryland carries out a test of the null hypothesis, saying the p-value, the probability of having the allergy, is 25%, using a 5% level of significance. Write down the alternative hypothesis. So he hasn't been clear about what his alternative hypothesis is. He's just said it's different. So if it's ever vague, just a disagreement, not how it's disagreement, then it's a two-tailed hypothesis test. So the alternative hypothesis would just be that p is different from 0.25 rather than less than or greater than. Then it says, can we find the critical region for this test? You should state the probability associated with each tail, which should be as close to as possible 2.5%. So we don't have to go strictly below 2.5% if it means we can get closer to 2.5%. So what I would do here is I would go to my my distribution function in my calculator, and to find critical regions, it's quite nice to use the list function. You can type in lots of values and get multiple calculations done for you at the same time. So let's type in a few values to try and get the lower tail. So I'm going to go up to 7, see if that gets us close enough to we go over 2.5% and under to see where the critical region would be. So the n is 50, there's a sample size of 50. The p-value is 0.25. So let's see if we get to 2.5%. This all looks too small at the moment. No, we can see we actually do. So let's write this down. So for part B, the probability x is less than or equal to 6 is 0.0193. 0.0193. And the probability x is less than or equal to 7 is 0.0452. So that's 1.93%. This is 4.52%. So in this case, actually, the closest one is under the 2.5% anyway. So the bottom part of the critical region would be this guy. So critical region is x is less than or equal to 6 with a probability of 1.93%. Then let's look for the upper 2.5%. So because we're accumulating from 0, that's going to look like the bottom 97.5%. So we're going to have to go quite far higher up. So let's start from like 25. Let's say let's go 25, 26, 27, and just see where that lands us in terms of probabilities. That's way too high. We're already at 99%. So let's go back. Let's shift these down. Let's say 20 and 21. See how close that gets us to the 97.5% threshold. We run the calculation again. Okay, so that's actually still a little bit too high. So let's do a few values now. Let's start from 15, and we'll go up to 19. Oops, sorry, 19. So running that calculation now. So we can see we actually crossed the threshold between 18 and 19. So again, let's write those down so we don't get confused. So the probability x is less than or equal to 18 is a 0.9712. We need to flip that if we're looking for the upper tail. So that would imply the probability x is greater than or equal to 19 is 0.0288. And if we go one up, just to double check, so probability x is less than or equal to 19. In our calculator, that's 0.986. That would be the if we flip it over again, that's probability x is greater than or equal to 20 is equal to 0.014. Good. Okay, so we can see the one that's closest to 2.5% is the 19. So the upper tail, the critical region, is the x is greater than or equal to 19. And that is 2.88%. And let's just be clear, like the total critical region is x is less than or equal to 6. And x is greater than or equal to 19. Then it says, state the actual probability of incorrectly rejecting H0. So incorrectly rejecting H0 means that H0 is true. So that is the probability of landing in the critical region, even though we've got the right hypothesis. Yeah. So that's basically just the probabilities of our tails that we worked out. Yeah. So part C would be our 1.93% plus the 2.88%. So if we go and calculate that, 1.93, 2.88 is 4.81%. Then it says that Ryland finds that 10 of the adults in his sample have the allergy. So that's our test statistic. We need to compare that to our critical region to see if it's statistically significant result. So 10 actually is not in the critical region. So there is insufficient evidence to reject the null hypothesis. Or let's be clear. X equals 10 is not in the critical region. Not in critical region. And therefore, there is insufficient evidence to suggest the proportion of adults with the allergy is different from 25%. Moving on to the last question. Question 5 says, Julia selects 3 letters at random, one at a time without replacement from the word variance. The discrete random variable x represents the number of times she selects a letter A. Find the complete probability distribution of x. Well, the probability distribution shows all the possible values for the random variable and the corresponding probabilities of obtaining that value for the random variable. So first, let's write out what the possible values are. So let's say little x for the individual values of our random variable big X. So there is a chance she could have 0 A's selected. Yeah, she could pick, for example, V, R, and I, and then she would have 0. Then there's a chance she could pick 1. There's a chance she could pick 2. But she can't pick 3. There aren't enough. So it could be 0, 1, or 2. And if you want to think about all the possible combinations, that's where things could get a bit tricky. But the clever way to think about this is, if we're just caring about A's, then you want to think about the events as she can either pick an A or not pick an A in each draw. So if she's going to select 0 A's, you got to think, okay, well on the first pick, this is probably x equals x. On the first pick, there are how many non-A's? So there's 1, 2, 3, 4, 5, 6. So there's 6 out of a total 1, 2, 3, 4, 5, 6, 7, 8 letters. And then she has to pick an A, or sorry, not pick an A 2 more times. So on the second pick, it's going to be 5 out of 7 as a probability to not pick the A. And on the last pick, it's going to be 4 out of 6. So we can run that through the calculator. What does that give us? 6 over 8 times 5 over 7 times 4 over 6, which is 5 on 14. Then the probability x equals 1, we have to be a little bit careful because there's 3 different ways that could happen, right? She could pick the A on the first, second, or third go. But if we think about it, that's not going to really, it's not going to really matter. Oh, actually, let's write it out to be careful. So on the first, let's say she picks it on the first draw. That would be 2 in 8. And then she'd have to pick not an A twice. So it would be 2 in 8 times the remaining letters. That would be 6 in 7. And then times 5 in 6. That would be the first possible option. Then the second one would be where she picks it on the second go round, right? So let's say she does, so the first one is not an A, so that'd be 6 in 8. Then she does pick the A, which would be 2 in 7. And then the last one would be she doesn't pick an A again, so there'd be 5 non-A's left out of a total 6 numbers. But if we look at this guy compared to this, it's what I said, it's not going to actually matter. Those sums are going to come to the same thing because all that's happened is the numerators have been reordered, right? So basically it's just 3 lots of this because we've got to account for the last draw. So we're going to just, if I just forget about this for a second, we're going to take this guy and times him by 3. That's going to be quicker in our calculator. So we'll have 2 over 8 times 6 over 7 times 5 over 6. That's the probability of her only selecting 1A And this can happen 3 different ways, so we're going to multiply this by 3, which is 15 on 28. And now we could repeat the same logic if we want to, and think about all the ways she could pick 2 A's. But what would be quicker now is we just use the fact that all probability distributions, their probabilities must sum to 1, right? So if we sum these 2 guys and take it away from 1, we would get the remaining probability available for the last option. Let's do 1 minus our answer that we just got there, and then minus the 5 on 14. We get 3 and 28 left as the option for picking 2 A's. Okay, then moving on, it says Yuki selects 10 letters at random, one at a time with replacement from the word deviation. Find the probability that he selects the letter E at least 4 times. So that's with replacement now. So there's a couple ways we could go about this. Let's just think about the quickest way. I think it would be easier. Well, actually, no. This is just a binomial distribution now, isn't it? Because if we replace the letters, the probability of selecting an E is constant, isn't it? So let's define a random variable. Let's call y the number of E's selected. And then our sample size, well, it's binomially distributed, and the sample size is Yuki picks 10 letters, and because she replaces the letters every time, the probability is constant of picking the E. So it would be 1 in, how many letters are in deviation? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 in 9 every time she selects a letter. And we're interested in the probability that y is greater than or equal to 4, which we could calculate as 1 minus the probability y is less than or equal to 3. And we can do that just with the CD distribution in our calculator. So CD variable, just because I'm interested in calculating one value only. So 3 and a sample size of 10 and a p-value of 1 in 9. So that means we'd have 1 minus 0.9815. So our answer is going to be 0.018. Let's put another decimal point in actually, so 157 here. So 1843. So to 3 significant figures, it's going to be 0.0184. Okay, so here we are at the front of the mechanics section now. Question 1 is a VT graph. It's about 2 children, Pat and Sam, running a race. It says Pat accelerates at a constant rate until reaching 4 meters per second and then maintains 4 meters per second until crossing the finish line. That's all on the diagram. It says Sam accelerates at a constant rate of 1 meter per second squared. So let's make a note of that. So for Sam, his acceleration, which is going to be at the start, but quite obvious, 1 meter per second squared. And it says both children take 27.5 seconds. That's on the diagram. Velocity time graphs shown in figure 1 describe the model of the motion of each child from the instant they start to the instant they cross the finish line together. Using the model, explain why the areas under the 2 graphs are equal. Well, the area under a VT graph is your displacement, or distance traveled. In this case, they're the same thing, and they both run the same race. So they're both same length of race. That's why the areas are the same. So A, they both run the same distance. That's the reason. Then it says find the acceleration of Pat during the first 5 seconds. Well, for Pat, we actually know everything we need to calculate that. The gradient gives us acceleration, and it's just a straight line, so we can do the rise over the run. So for part B, he accelerates 4 meters per second in 5 seconds. That'd be 0.8 meters per second squared. For part C, it says find in meters the length of the race. Well, we just said a minute ago the distance is represented by the area under the graph, and we have everything we need for Pat's graph to be able to calculate that area. So let's do it as a trapezium. We've got the parallel sides here, and then the perpendicular distance between them is 4. So the distance is a half the sum of the parallel sides times the distance between them, which would be a half of the bottom is the full 27.5. The top is the 27.5 minus the first 5 seconds. That's 22.5. And then the distance between them is 4. That's the height of the graph, 4 meters per second. So times 4. We run that through the calculator. We have 0.5 times 27.5 plus 22.5, all times 4. That's equal to 100. 100 meters, I should say. Find the value of x. Okay, so what information have we got? We know that the area under Sam's graph is the same as Paul's graph, and we also know the gradient for Sam's graph. So let's use that information to create some equations. So first off, if we use the acceleration, we know the gradient is 1, or the acceleration is 1, so 1 must equal x over, let's call this value here, where he stops accelerating t. So 1 is x over t, or in other words, x equals t. And then if we use the same scheme to calculate the area under his graph, it would be the full length, well, the distance is 100 because they run the same race, and then it's a half times the full length of 27.5, plus we've got the full 27.5 minus t, so plus 27.5 minus t, all times the height of this graph, which is just x. If we simplify that, we'd have 100 equals a half times 2 lots of 27.5 is 55. And then we'd have minus t, and then a multiplying x. So now we have 2 equations with 2 variables. We can include this and this. And 2 equations, 2 variables means we can solve simultaneously. So we're after x, so let's substitute out t for x in our second equation. Then we have 100 equals a half 55 minus x times x. Let's this is going to be a quadratic when we expand, so let's expand it and bring it all to one side. So we'd have if I bring the 2 to the other side, we'd have 200 equals 55x minus x squared, or x squared minus 55x plus 200 equals 0. If we run that through our quadratic solver, so use the equation function, polynomial, choose the quadratic option, and our coefficients are 1, minus 55, and 200. And that's our first solution. That looks a bit big. Let's just check. Yeah, 51, that doesn't seem reasonable. And if we look at our graph, we know x actually has to be less than 4. So let's look at the second solution. Put that as a decimal. That seems much more reasonable. So x equals 3.92 meters per second. The 3 significant figures. Moving on now to the next question, question 2. It says a small stone is projected vertically upwards with speed 39.2 meters per second from a point O. The stone is modeled as a particle moving freely under gravity from when it is projected until it hits the ground 10 seconds later. Using the model, find the height of O above ground. So first off, let's draw a little diagram. So let's say here's the ground. Here's the ground. Let's say here's point O. And it starts with a speed 39.2 meters per second. And it's modeled as moving freely under gravity. So that means the acceleration is 9.8 back down towards the ground, as the only force is gravity. And if the acceleration is constant, that means we're allowed to use SUVAT. So what we're after is this distance h. And we know it hits the ground here when t equals 10, if we consider this to be t equals 0 when it first leaves the O. So let's write a SUVAT for part A. We have S is what we're trying to find. Let's call that H. Let's consider up to be positive. So U would then be 39.2. A would be negative as it's going down, so minus 9.8. And then T is 10. And we're looking for an equation then without V. If we want to find S, that would be S equals UT plus a half AT squared. So we're going to be doing 39.2 times 10 minus, well, it's plus, but the minus is going to come from the minus 9.8. So I'll just write minus a half times 9.8 times 10 squared. Plugging that in the calculator. Got 39.2 times 10 minus 0.5 times 9.8 times 10 squared. Gives us minus 98, which is, if you're worried about finding a negative, that's not something to worry about because our displacement was down in the scenario and we took up as positive. So we were expecting to get a negative actually. So S is 98 meters, which is our height above the ground. Good. The total length of time for which the speed of the stone is less than or equal to 24.5 meters per second. Okay, well, let's find the amount of time, like at what times it's equal to that. And then we can think about how long it was below that time, below that speed for. So let's do another SUVAT now, where the things we know still are the initial speed. If we take up as positive again, we'll have 39.8. And we're trying to find when the speed of the stone, sorry, B is not 39.8, U is 39.8. And actually, it could be plus or minus 24.5, couldn't it? Because it's going to be going up at one point at that speed and then coming back down at one point from that speed, So plus or minus 24.5, and we'll see how the plus or minus affects our calculation. And A is still down, so that'll be minus 9.8. And we're after the times in this case. So T equals, T is just T, which is what we're trying to find. And we're using an equation without S then if we would like to find T. So V equals U plus AT, or T equals V minus U over A. That means we have plus or minus 24.5 minus U, which is 39.8, all over minus 9.8. Let's calculate those two possible values. So T, we do the positive one first, would be 24.5 minus 39.8. All over minus 9.8. which gives us a time of 1.56. And then the second one, if we think about the negative value, which is when it would be coming back down, if you think about it. So, oops. Okay, one, good. So make this 24.5 a minus now to get the other time. That gives us 6.56. So let's just to make sense of this, let's think about what's happening again. We start with our guy at O. It goes up and it comes back down. And it's going to go up and at some point be at a speed of 24.5 going up. That's going to be the first time, right? T equals 1.56. And then some later time, it will be going back down at the same speed, which is 24.5, but down in that case. And that is going to be 6.56. And then our question is interested, the total length of time for which the speed of the stone is less than or equal to. That's always going to be this section above, right? So at the very top, it's 0 meters per second. And as like, if you go down here, it's going to be accelerating the whole way. So it's going to be greater than, right? And it started off greater than in this section. So it's the time in between those two times. So if we do this one time minus the other, we'll get the length of this green part of the journey here in time. That'd be 6.56 minus 1.5. We do, yeah, let's subtract the minus 1.5, sorry, 1.56, excuse me. Put that as a decimal. We get 5.00 seconds. Okay, then it says, state one refinement that could be made to the model that would make your answer to part A more accurate. So what are some assumptions we've made? We've modeled it as something as a particle, so we could think about that. We could, like, if it had some size, we'd have to think about the dimensions of the ball, because it wouldn't be the full distance. It would be the full distance minus the radius of the ball would be the distance it has to travel to get to hit the ground. Or we could also think, well, in the reality, there's drag when we throw objects through the atmosphere. So I'll put that as the answer. So one refinement is to include a resistance to motion, a force that resists motion. That's part C. Include a force that resists motion. Moving on now to question 3. It says a fixed point O lies on a straight line. A particle P moves along the straight line such that at time t, where t is greater than or equal to 0, after passing through O, the velocity of p is v meters per second. And we've got velocity as a function of time. As soon as we see functions of time for our velocity, displacement, or acceleration, we want to think it's a variable acceleration question. So we want to use our calculus to convert between the functions. Part A is asking when it comes to instantaneous rest. So that's actually a question for the velocity function. If we're at rest, our velocity is 0. We just need to solve for when v equals 0. That would say 15 minus t squared minus 2t equals 0. Or I don't like looking at negative quadratics, so I'm going to move this around and say it's t squared plus 2t minus 15 equals 0. And that actually factorizes quite nicely. We could factorize that as t plus 5 and then t minus 3, which gives us solutions of t minus 5, but that's outside the scope of the model because t needs to be positive. So the only acceptable solution would be t equals 3, and it's measured in seconds, so t equals 3 seconds. Then it says find the magnitude of acceleration. Well, to get the acceleration, first we're going to need the velocity. Sorry, we need the acceleration function to. Sorry, guys, I just realized in part A, It says verify, so to be really quick, I could have just plugged in t equals 3. That's my mistake, I didn't read the question. But this demonstrates it fine as well. Yeah, for part B, we need the acceleration function. So we need to differentiate to get the acceleration function. So acceleration as a function of time is going to be minus 2t, and then minus 2. And then we just want the acceleration at t equals 3. So if we plug in t equals 3, so a of 3 would be minus 2 times 3 minus 2. That's minus 6 minus 2, which is minus 8 meters per second squared. They asked for the magnitude, so let's just fix that and forget about the sign. So it's 8 meters per second squared. Oh. Sorry guys, managed to just go onto the wrong document. There we go. Oh no, still the wrong document. There we go, there we were. Right, final part then. Find the total distance traveled by p in the interval from 0 to 4. Okay, so we can find the distance as the area under the graph, but we have to just be careful because if it changes direction at all, then displacement isn't going to be the same as distance traveled. Yeah, because if we change direction, the distance is going to cancel out because displacement just cares about if I go forwards and backwards cancel out, but distance doesn't care about that. So whenever you get this question about distance, I recommend you draw the velocity function. So actually what I did here is going to be helpful. We know the roots for our velocity function. So if I draw this in, it's a negative quadratic with roots of -5 and 3. So look like that. Not very good, well drawn, but you see what I'm trying to do. And actually, this is a problem now, because over the interval from 0 to 4 that we're interested in, some of that area is negative. So we need to evaluate the positive and negative area separately if we don't want them to cancel out to give us displacement instead of distance. So to do that, we're going to integrate from 0 to 3. So our distance traveled is going to be the integral from 0 to 3 of our velocity function, so 15 minus t squared plus minus 2t dt. And then we're going to have to think about adding the magnitude of the integral from 3 to 4 of the same function. So first, if we integrate, we get 15t minus a third of t cubed minus t squared. And that is from 0 to 3. So we have to add the magnitude of that same thing, but with different limits. So 15t, sorry, I just spotted a mistake here. That should say minus a third t squared, shouldn't it? T cubed, excuse me. So minus a third t cubed. And then minus t squared from 3 to 4. So this first one, fortunately, is quite simple. The 0 limit is just going to come to nothing. So if we just plug in the 3, if I do that in the calculator, we'd have 3 times 15. Minus a third times 3 to the power of 3. And then minus 3 squared. That gives us 27 for that first bit. Then we need to evaluate this. I'm going to write the limits out for that one, just so I don't make a mistake. It'd be plus the magnitude of magnitude, guys, just means I'm going to ignore the sign later. I'm going to make sure it's positive so they don't cancel out. So going to be 15 times 4 minus a third times 4 cubed minus 4 squared. And then it's minus the other limit, so that's 15 times 3 minus a third of 3 cubed minus 3 squared. So if I type that all in the calculator in separate brackets, we've got 15 times 4 minus a third times 4 cubed then minus 4 squared for that first limit. Close the big bracket. Now evaluate the second limit. So another bracket, 15 times 3. Then minus 1 over 3 times 3 cubed. Minus 3 squared. Close all that. We get a minus like we were anticipating, but now we're going to add that as a positive. So 27 plus positive 13 over 3. If we add, let's just times that by minus 1 to make it a positive, and then we'll add 27. That's 94 over 3. Or as a decimal, that is 31.3 meters. The 3 significant figures. Okay, moving on to the next question. We've got a car towing a trailer. It says the car is mass of 1,200 kilos. The trailer is mass 400 kilos. They're both on the diagram. It says the resistance to motion of the car is modeled as a constant force of magnitude 2r. So let's assume the car is moving forwards. And then there's a force of 2r acting on the car to the left. The resistance to motion of the trailer is modeled as a constant force of magnitude r. So there's a force r going to the left on the trailer. The rope is modeled as being light and inextensible. So light means the tension is the same magnitude everywhere in the string. And inextensible means the accelerations of the car and the trailer are going to have to be the same in magnitude also. There's the acceleration of the car is a meters per second squared. The driving force of the engine of the car is 7,400 newtons. And then it says the tension in the tow rope is 2,400 newtons. So on the car, that would be acting to the left as 2,400. On the trailer, it would be acting to the right, obviously, if it's going to be pulled along to match the motion of the car. And there's nothing really going on vertically, so it's not really going to be important to mark down those forces. Using the model, find the value of A. So we have two unknowns. We have A and R, meaning we're going to need two equations. So we can achieve that by just treating the car and the trailer separately and doing a model individually for them. So if we do the trailer first, doing F equals MA, we're going to have 2,400 minus R, this is me taking to the right, being positive. So 2,400 minus R is going to equal 400A. And if we do the same thing now, but for the car, F equals MA, we're going to have 7,400 minus 2,400 minus the 2R equals 1,200A. And now we can see we've got two equations and two unknowns, so we can solve simultaneously. Let's just simplify this second equation down. This gives us 5,000 minus 2R equals 1200a. And then actually we can get an equation, or we want to find r. Sorry, we want to find a. So let's rearrange this guy for r. The first guy becomes r would equal 2400 minus 400a. If we plug that into our second equation for the car, we have 5000 minus 2 lots of 2400 minus 2r equals 1200a. Expanding out, we would have 5000 minus 4800. Sorry, what have I written here? I shouldn't have written 2r here, should I? That should be 400a. Sorry about that, guys. Just clean that up. 2400 minus 400a. Again, guys, I'm just substituting this r into our equation for the car here. Or, well, here, actually. Sorry for the confusion. So 2400 minus 400a equals 1200a. Good. So expanding out, it is going to be 5000 minus 4800 minus, oh, sorry, there's a double minus, so plus 800a equals 1200a. If we simplify that, we're going to have 200. And if we brought the 800a to the other side, that would be 400a. That means a is going to be 200 over 400, or in other words, a half, so 0.5 meters per second squared. Okay, then it says, in a refined model, the rope is modeled as having mass, and the acceleration of the car is found to be a1. Show how the value of a1 compares with the value of a. Well, if we were going to do that, we're going to need to think about how it's going to change our calculation, right? So what we could do to incorporate the the tension, sorry, the rope into our calculation is we could think about the whole system, and then the reaction forces wouldn't actually change. But the masses would, right? So if the mass of the systems goes up, but the forces don't really change on the system, then the acceleration is going to have to go down, right? F over m gives us the acceleration. If the mass is bigger, but the force is the same, we're going to get a smaller number. So there's state, actually, so we don't need to even explain ourselves. So we'll just say the a1, which would be the new acceleration, would be smaller. This is for part B. So a1 would be smaller than a. Then part C, it says state one limitation of the model used for the resistance to motion of the car. So the resistance to motion is modeled as being constant, but air resistance doesn't do that. It changes with your speed. So it's modeled with as a constant. Sorry, air resistance is modeled as a constant, or resistance to motion is modeled as a constant. As a constant. Yeah, and it should change, or it should be dependent on the speed. So it should be dependent on speed. That's the end of the video, guys. I hope you found it helpful. If you did, please drop it a like, that helps me out a lot. and consider subscribing to the channel to find out when I release new videos. Thanks, and I'll see you in the next one.